Hi, Alistair. If air enters a evaporative cooler at 1 atm, 35-degree dry bulb temperature, and 20% relative humidity at a constant volume flow rate of 4 cubic meter per minute, when it leaves at 90% relative humidity, what will be the dry bulb temperature of the air?
Okay, well look, to answer that question, we need to look at the psychrometric chart. So let's just draw a very rough psychrometric chart. Now when answering this question, of course, you'd need to look up a psychrometric chart, but we're just going to draw a quick one here. All right, so very roughly. Now, what's the x-axis going to be here?
That will be the dry bulb temperature.
Okay, so let's just do one that says 0 degrees Celsius. So this will be dry bulb temperature, degrees Celsius, and we'll see if we can do it. There we go. Something like that, great. And what about the vertical axis? What will that be?
Would that be the specific humidity?
Specific humidity, very good. Okay, so there's specific humidity. Now, normally this comes in all sorts of units, but let's use for this example grams per kilogram. And we've got to be always careful here. We really should say kilogram of dry air. Everything is per kilogram of dry air when we talk about specific humidity or absolute. Let's call it, I like specific because that always means something. Specific humidity or specific enthalpy, anything like that means you're dividing by 1 kilogram of dry air. Whatever the amount of air you've got, work out how many kilograms of dry air and you divide by that. That tells you how many, in this case, the specific humidity, how many grams of water vapor per kilogram of dry air. Okay, great. Well, look, we won't label that for now because we'll come to do that in a minute. Now, our starting conditions were 35 degrees and 20% relative humidity, and we want to look at what happens at 90% relative humidity. So let's draw 90% relative humidity. So I'm drawing in the dashed line here very roughly. This is relative humidity as a percentage. So there's 90%. 100% of course is that solid line up the top there. Let's also draw in, we're just 90% of that. Let's go over here and we'll very roughly draw in 20% relative humidity. Great. Not the best psychrometric chart ever, but it will do. Okay, so we're at 35 degrees dry bulb temperature and we're at 20% relative humidity. So that means our starting point of our inlet conditions, our inlet air, is, well, roughly there. There we have it. Now, when we pass air, outside air that's like this, very dry, 20% relative humidity is very dry. When we pass it through an evaporative cooler, that air will pick up moisture from the evaporative cooler and become more humid, but it will also cool down. And so the air will follow a line, a constant wet bulb line or a constant enthalpy. Those two lines on the psychrometric chart are fairly similar. Constant enthalpy means no added energy from outside. So that's what we're going to draw now. And it's roughly a line that looks something like that. There's our constant wet bulb line. Okay, great. So we've got our inlet conditions, 35 degrees, 20% relative humidity. We go along, as the air moves through the evaporative cooler, it moves along this line until we reach the point where we get to 90% relative humidity. Now, the question was asking us, as the air exits the evaporative cooler. What's the dry bulb temperature? Well, to find that, we just drop down here and we find that we have a dry bulb temperature. If we look on our psychrometric chart of 20.5 degrees Celsius, and that's pretty much all we need to answer. We might also just have a look here and see, just out of interest, the wet bulb temperature. It turns out to be, I think, 19.5 degrees Celsius. And I think that's all we need to answer for the first part of our question. Right.
Oh, thank you, Alistair.
That's all right.
I have another question for you.
Yes?
What about if we're trying to find the required rate of water supply to the evaporated cooler for this process?
Great. Okay, so because the air is dry at the start and more humid by the end, that means it's actually, we're adding moisture to the air. So we add moisture to the air to cool it down. Let's have a look and see how that's happening. So at our starting conditions, what we would do is that we would look at 35 degrees C dry bulb temperature and 20% relative humidity. To find out the specific humidity of the air, we would go across here to the vertical axis for specific humidity and find that we would get 7.4 grams per kilogram. I won't put the dry air, but there it is. Now that number may be a little bit varied depending on which chart you're using and how accurately you can read off the chart, but to within a few percent, you should be able to get a number something like that, 7.4 grams per kilogram from the psychrometric chart. The other piece of information, of course, that we need is what is this? So that's omega 1. We need the outlet conditions. We want to know the specific humidity of the outlet air. We come across to the vertical axis and find omega 2 will be equal to something like 13.7 grams per kilogram. And I'm leaving off the dry air because I'm assuming everyone's happy with that. So if we look at the difference, omega 2 minus omega 1, that's going to come out at 6.3 grams per kilogram of dry air. So that's a useful number for us, but we still need to know something else. Now, we're asked what's the required rate of water supply to the evaporative cooler. Well, what we need to do next is to work out what is the specific volume of the inlet air. So again, we would look on the chart. Now there's lots of information on a psychrometric chart, but there will be a line, something like this, that will tell us that the specific volume at the inlet will be 0.887, making a mess of my chart here, but hopefully you can read that. Cubic meters per kilogram of dry air.
Oh, I see. So we're already given the volume flow rate. Do we need to find the mass flow rate from this information?
Yeah, so we better find the mass flow rate. All right, so now our diagram's getting very busy. So let's just step away for a minute and have a look at that. So we've got ourselves the difference in the specific humidity. We've got our number here of 0.887 is the specific volume. Now we need to work out, as Jinyi was saying, we need to work out the mass flow rate. So that's important. So how are we going to work that out, Jinyi? What do we need to work out the mass flow rate?
Well, from the question we were given that the volume flow rate will be 0.067 cubic meter per second.
Okay, let's write that up here over here. So we've got a volume flow rate of 0.06
cubic meter per second.
Cubic meters per second, terrific. So for us to work out the mass flow rate, we need to then just simply say our mass flow rate is going to be given by our volume flow rate divided by our specific volume at, oops, that's not right. Good job, I've got this little thing here. We need to have the volume flow rate divided by the specific volume, and that will give us the mass flow rate. So let's do these numbers now, and always good to keep the units. So 0.067 cubic meters per second. We're going to divide by 0.887 cubic meters per kilogram. When we look at the units here, cubic meters will cancel out, kilograms will be flipped up, and that'll give us the number that we're after, which is 0.076 kilograms per second. Now, an important thing that I've left off is that is the mass flow rate of our dry air. We're working everything out on a dry air basis. Remember that we said this was, the specific volume is always cubic meters per kilogram. Better put that in there. Kilogram of dry air, just to emphasize the point. So that kilogram that gets left when we do the calculation is kilogram of dry air, and that's explicitly telling us we've got the mass flow rate of the dry air moving through the system. So mass is always conserved. That's why we work it out this way. If we work out that we've got usually the volume flow rate here, we often know that at the inlet. That's the inlet specification. We know that volume flow rate. We work out the mass flow rate of the dry air at the inlet. That will be conserved all the way through the system, which is why we like to work with on a dry air basis. Okay, so here's our final number, the mass flow rate of the dry air. Fantastic. Now we're almost there. Now, what happens is that we're looking for how much water is being added, how much water vapor is being added to the air as it moves through the evaporative cooler. We've found that out over here. We've got the difference between the outlet at position number 2 here. There's our outlet. Oop. My pen is getting a bit dry. And this is, that's better. The inlet, that's the outlet. Now the difference in that specific humidity tells us that we've got 6.3 grams per kilogram being added. We want to know the rate at which we need to supply water. So that will just simply be what is the supply mass flow rate of water. That's going to be equal to the mass flow rate of the dry air multiplied by omega 2 minus omega 1. Let's just write those numbers in, and we have 0.076 kilograms of dry air per second moving through the system, and we're multiplying by 6.3 grams of water per kilogram of dry air that's required. So let's work that out. That works out to be 0.48 grams, to be explicit, grams of water kilograms of dry air cancels. We have 0.48 grams of water per second is the mass flow rate required to keep the evaporative cooler working. Well, there we have it. I think that's the end.
Thank you. Thank you, Alistair, for that.
No worries. All good.
Alistair, most building elements consist of more than one material. For example, a wall of a home could consist of outer layer brick, concrete, or wood, possibly some insulation, and finally a lining material like gyprock. Such a material have a multi-layer. So, how do we calculate the heat transfer through such a material?
Okay, well look, I think the thing we should do is we should look at what's the steady state heat transfer through a multi-layer wall. So let's draw that wall first off. So we won't worry too much. We'll just have 3 different layers that look like something like this. We won't specify exactly what those materials are. We just want to say that they might have thickness L1, L2, L3, and they might have conductivity, thermal conductivity K1, K2, K3. So this is a very general treatment. Now, when we're dealing with materials like this, we've got, in this case, 3 materials connected together in series. We'll talk about that in a minute. But the important point that we really need to be clear about is we want to know the temperatures right at that interface there. And we're assuming this is all uniform. And so we've just got a one-dimensional problem. We're not worrying about 2 dimensions or 3 dimensions, just a one-dimensional problem. Here's T1. T2 is the temperature between the material, between layer 1 and layer 2, T3 and T4. Okay, great. Now, I think it's always useful to understand that what we're dealing with here is a thermal resistance problem. So let's look at the thermal resistance here. Okay, so there's a thermal resistance. So we'll have thermal resistance 1, 2, and 3. We'll talk some more about them in a minute, but each of those thermal resistances are associated with each of the layers of the material that we have in our wall. And of course, T1, T2, T3, and T4 correspond to the temperatures as indicated on the thermal resistance diagram there. All right, so the question asks us, well, maybe we should just have a look at that. Does that, let's step over this way. Does that make sense? We've got 3 layers.
Yes.
3 different thermal, all these materials can have different thicknesses, different thermal conductivities, and we represent it as a thermal resistance.
Okay, Alistair. So can we find maybe an expression based on the temperature of the first layer and the last layer in terms of the rate of heat transfer through the wall?
Yeah, so okay, so I think in the question as it's written, we're told that the rate of heat transfer through this multi-layer wall is given by Q dot conductivity, and it's going to be equal to, sorry, need this one. Okay, so we need Q dot conductivity. We're told that the equation that describes the heat transfer is T1 minus T4 divided by R1 plus R2 plus R3. Or we could write that as T1 minus T4 on top of R total. Now, well, R total is just simply the sum R1 plus R2 plus R3. All right, so let's see how we go about doing that. So the first thing we ask ourselves, through our thermal resistance network, what we're looking at is the rate at which heat is conducted through those three layers. Of course, because the thermal resistances are in series, what that means is that the rate at which heat transfers through each thermal resistance has to be the same in each thermal resistance. It's like currents flowing through resistors in series, heat flowing through thermal resistances in series. The current through each resistance, the rate of heat flow through each resistance, thermal resistance, has to be the same. So to start, how do we work this out? Well, let's work this out. We'll start with looking at, we can say Q conductivity is going to be equal to T1 minus T2 on top of R1 and that's just going to be equal to, because it's the same, because they're all in series, if we have T2 minus, if we consider the second thermal resistance, we can write that expression, and the third Okay, so now something that we should have mentioned is that what is a thermal resistance? Well, if we come over here, that thermal resistance is for each layer given by that expression. What's the thickness of each layer? L. What's the thermal conductivity? K for each layer. L divided by K divided by the area of the wall that we're considering. So that gives us a thermal resistance. Okay, so useful for us just to have a look and see what are the units of the thermal resistance that we're working with here. Well, we'll just put this bracket here. Length, of course, is going to be typically in meters. K is going to be watts per meter per degree Kelvin or Celsius temperature difference multiplied by meters squared for area. So when we look at all of that, what do we end up with? This meter and this meter cancel out with this meter squared. So this really becomes, the units here are Kelvin per watt, or we could have written degrees C per watt. Make that a bit bigger. Either of those is equivalent because we're dealing with differences in temperature, so delta temperature, Kelvin or degrees Celsius, same thing. Okay, all right, so let's go back now. We've got ourselves our equations here. The simple way to solve this is just to say, well, okay, because the rate of thermal conductivity through each resistance is the same, we just multiply this out now for each expression, and we can find this. If we write this, for example, Q dot conductivity multiplied by R1 is equal to T1 minus T2. And we can write that again for R2 and for R3. So we have three equations. 1, 2, 3 equations. Let's just add 1 plus 2 plus 3 and see what we get. Well, we find the left-hand sides add together. I've taken Q conductivity outside the brackets and added together R1 plus R2 plus R3. Now let's add the right-hand side. When we add the right-hand side, have a look at that right-hand side. If we add those all together, what we've got here is minus T2 plus T2. So they're going to cancel. Minus T3 plus T3. They're going to cancel. But we're just left then with T1 minus T4. And then we just simply rearrange that. To give us the answer that we were looking for from the start. Better get that right. Now, that's a little bit of mathematics, but I think it's a nice, simple bit of mathematics, and you probably don't see too many textbooks that do this proof, so I'm happy to show this one.
Oh, thank you, Alistair, for the proof. That was great. If we have a room with a dimension of 8 meter by 8 meter with a 2 meter height of wall, the wall consists of 13 millimeter of gyprock, 100 millimeter of insulation bat, and 100 millimeter of brick. So if the inside wall temperature is 20 degrees and the outside wall temperature is 10 degrees Celsius, can we work out the rate of heat transfer through the wall and maybe the temperature profile for this wall?
Yeah, great. Well, look, that's something we can do. Now that we've done that first part of the question, let's tackle this second part. So, first of all, we need to just draw up our table, and we need to have layer. So we'll have that first layer gyprock. The second layer is the insulation, and the outer layer is brick. Very typical construction. Let's write up now the thermal conductivity. Now, we need the thermal conductivity. We need the thickness of the layer. We'll write that up in millimeters. Of course, we need to calculate in meters. Might just go a bit bigger here. And in the end, we want to calculate our thermal resistance in degrees C per watt. So, for gyprock, we have a value of 0.81 watts per meter per degree C. Notice that for brick and gyprock, I'll jump down to the brick layer, very similar. Per meter of material, the heat transfer per degree C is very, very similar. So solids often have numbers for thermal conductivity close to 1, close to 1. Now, our insulation, though, is much smaller, an order of magnitude smaller, which indicates we're no longer dealing with a solid material. For insulation, we're actually dealing here with trapped layers of air, which is why the thermal conductivity is that order of magnitude lower than the gyprock or the brick. Okay, now the gyprock is only typically 13 millimeters thick. In this case, we've got 100 millimeters thickness of insulation and 100 millimeters of the brick. And we just need to calculate using this expression what is the thermal resistance. So when you plug those numbers in, we get 0.0003 for the gyprock, 0.0347 for the insulation, and 0.0022. Now, something that I should have mentioned, of course, is what's the area of the wall. Done the calculation, but didn't tell you the area. Now, the area, of course, we've got 8 meters length of wall, 2 meters high, and we've got 4 walls. So that gives us a total of 64 square meters. So that's the value of the area of the walls that we're dealing with, which we needed when we're calculating the thermal resistance. Okay, so, all right, sorry about that. Now what we want to know is, well, for this multi-layer wall, what's the total thermal resistance? So here we have R1, R2, R3. We just need to add that up. And that's a bit of simple mathematics. It works out that 0.0371 degrees C per watt is the total thermal resistance, and we can see that the vast majority of that thermal resistance is coming from that insulation layer, which is probably something that we should expect. All right, so all we need now is to calculate how much heat will be transferred through our wall. Now we're told, what was the temperature of the inside of the wall?
That will be around 20 degrees.
So we're told the T1 is 20 degrees C, and we're told that the outside wall temperature T4 is
about 10 degrees.
10 degrees Celsius. So typical winter conditions in somewhere like Sydney. And now we just write down, and we can say from part A we had Q dot conductivity is going to be equal to T1 minus T4 on top of R total. We can just write all of that in. So that's 20 minus 10 on top of 0.0371, and that will give us 269.2 watts. And that's the total amount of heat going out through our wall. All right. Now, the next part of the question, what do we need to find out now?
We'll need to find out the temperature profile through each interface.
Okay, great. Well, we know that temperature 1 on the inside of the wall is 20 degrees Celsius, and we know the outside wall temperature is 10 degrees Celsius. Let's see how we can calculate the other temperatures that we don't know. So the only ones that we don't know, what don't we know? We know T1, we know T4, but T2 and T3 we don't know. Well, the good news is it's quite a simple calculation, so let's have a look and see how we can do this. So probably the easiest way that we can see it is to write down and say, well, we worked out before that Q conductivity is equal to T1 minus T2 on top of R1. That's just telling us that the temperature difference across our first layer, which has a thermal resistance R1, the rate of heat transfer through that is driven by the temperature difference and the thermal resistance. And that equation is simply the thermal equivalent of Ohm's law, if you like. Delta T corresponding to delta voltage, change in voltage. Q dot conductivity is corresponding to current. So that would be, oh, I can't resist, I'm going to write it. I equals delta V over R. There's our electrical analogy. So all we're going to do now is rearrange our thermal equation. We want to find out T2. We don't know T2. So T2 is just simply written down. We say T2 is going to be equal to T1 minus Q conductivity times R1. So that makes sense, which is great. So let's do that. So T1 is 20 degrees Celsius minus, now Q conductivity we had before is 269.2 watts multiplied by R1. Now what's our value for R1 is, well, it might be a bit rounded, 0.0003. Just check the number of significant figures that you've got there, but roughly that sort of number there. That's degrees C per watt. And so that tells us that we will have a value for T2 of 19.93 degrees C. Just be careful. This number here, just check significant digits. There might be a few more digits needed there just to get the right answer when you calculate this. But this is the correct answer. So, interesting there, we have only a small temperature difference across that inner layer, that first layer. Let's see what happens on the next layer. Well, we want to calculate T3. So just as we wrote this expression for T2, we can write a similar expression for T3. That's just simply telling us what the temperature drop due to the flow of heat conducting through our thermal resistance R2, and that temperature T3 will be a result of this expression. So let's put the numbers in. So we've got T2 is 19.93 degrees Celsius. We've got the same amount of heat flowing through our second thermal resistance, 269.2 watts, but we're now dropping it across, well, we've got a thermal resistance R2, which is 0.0347 degrees C per watt. So that gives us T3 is going to be 10.6 degrees Celsius. So we can see most of the temperature difference going from inside the room to outside the room. Most of the temperature difference is occurring across that second layer, that insulation layer. And I think we've pretty much answered the question now. All we'd need to do is to plot that temperature distribution across our wall, and we'll do that next. Okay, so all we need to do now is to draw temperature on the vertical axis. Let's do that. And we'll just draw, we'll start here at, we'll call this x is the distance through the wall. We'll call x equals 0. We'll do it in millimeters. So that's the inside surface of the wall. We then have, this is not so much to scale, 13 millimeters is our first layer. Then we have 113 millimeters for our second layer. So this is layer 1, layer 2, layer 3. Our brick, we have another 100 millimeters, so 213 millimeters. Let's plot the temperature. Well, we know that T4 is going to be 10 degrees Celsius, and we know that T1 is 20 degrees Celsius. Perhaps I'll put the dots on. 19.93 degrees Celsius is T2, and this one is 10.6 degrees Celsius. And so if we draw the line now, joining up those points, make those points a little bit bigger, we can see, as we would expect, that for steady state heat transfer, most of the temperature change is across the layer in the wall that has the highest thermal resistance. So that makes sense. It's the one that gives the most resistance to heat flow, so most of the temperature drop occurs across that. The other layers, the more thermally conductive layers, particularly the thinner layer, the thinner gyprock layer, less temperature drop across that. The 100 millimeters of brick, not much of a temperature drop across that, only 0.6 of a degree from T3 to T4, which indicates that brick, 100 millimeters of brick, really doesn't offer us much thermal resistance between inside and outside, and so won't help keep the heat in the building, which is what you want to do in winter. The thing that will really help keep heat in the building is that insulation layer.
Okay, so Alistair, what will happen if we take the insulation out?
Well, that's a good question, Ginny. Let's have a look and see. So let's just look at two-layer wall now. We'll have one layer with gyprock and the second layer with brick. And so now we're just considering our thermal resistance. We just have two layers, R1 and R2. So let's just write that down. We want to know what's the total thermal resistance. So that's just going to be now R1 plus, well, we'll call it R2, but this is now our brick layer. So we'll just use the numbers that we had before, and this is our gyprock layer. And if we take those numbers, we find that the R total is 0.000, well, I think we worked out in the break, slightly more digits was 0.000. This is the gyprock, is 0.00025, plus the brick was 0.0022, a little bit of rounding there, but we end up with approximately, well, 0.002, well, we better write it as 245 degrees C per watt. So then we can see that we're now an order of magnitude lower than the insulation case. All right, going back now, we need to calculate with this new situation, what's the rate at which heat will be conducted through this layer now, these two layers, delta T on top of R total, using delta T here, which we know is 10 degrees Celsius, divided by 0.00245, and that gives us now a value of, so considerably more heat is being conducted through a wall with no insulation, just the gyprock, just the brick. So under steady state conditions, we've got more, well, probably about a factor of 20 times more heat going through a wall with no insulation. Let's work out what the temperatures are at the various points in our wall. Now we already know we're told that this temperature, T1, is 20 degrees. So that would be typical of a room that's being heated in the winter. maintaining a constant temperature inside, we'd keep that wall temperature at something like 20 degrees C. We know that outside we've got 10 degrees C fixed, and we're interested in calculating what the temperature, the only one we don't know is T2. What's that? Well, again, we just make use of the thermal equivalent of Ohm's law. So the best way to do that is to say that we have T2 is just going to be equal to T1 minus the conductivity Q dot times R1. Now, we might think we've calculated this before, but what's changed is that we're calculating now with a new value of the rate of heat conducting through that thermal resistance. So let's see what that number comes out as. All right, so that's going to be 20 degrees C minus, we're carrying lots of significant digits here, but that's okay, multiplied by, now R1 is the gyprock layer, and it's 0.00025 degrees C per watt. And so this works out at, very approximately, gives us 19 degrees Celsius. So previously we had a very small temperature drop across gyprock layer. Now we've got a little bit more temperature drop across there, about a degree. So we get that, and then we'll see across the brick. So T2 is now 19 degrees Celsius, the inside wall at 20, the interface between the gyprock and the brick is 19 degrees C, and across the brick to the outside we go from 19 degrees C down to 10 degrees C. So what we can see here is that the brick now has the highest thermal resistance, so it has the highest temperature drop across it. Its thermal resistance is highest. Here's the brick's value. It's highest because it's the thickest layer. The thicker the layer, the higher the thermal resistance. But what we want to really see when we do the second calculation is in comparison to the first calculation when we had the insulation. When we were insulated, this Q conductivity, when we had insulation in the wall, what was that number? That was 269.2 watts. So the take-home point from that is that uninsulated walls will conduct a lot of heat, a lot more heat than insulated walls.